Good afternoon, everyone. I'm Peter Gillard from Fraser-Nash Consultancy. Thank you for joining this IMechE webinar on developing the UK nuclear fusion industry. This is a two-part webinar. Part 1 today gives a view from the UK public sector. Part 2, which is a week tomorrow, gives the private sector view. Today's webinar has been presented by Dan Wolff from UKAEA. Dan's been involved in fusion for the last 2 decades. He's been lead engineer for the UK's flagship fusion experiment MassDew and the European demo power plant design team. He's now part of the team delivering the Spherical Tokamak for energy production, or STEP, targeting putting electricity into the UK grid around 2040. Dan leads the team considering the commercialisation of fusion energy within the STEP programme. Dan's going to talk for 40 to 45 minutes, and we'll then have 15 minutes or so for questions. Please type any questions you have into the Ask Questions tab in the webinar window. You can do that throughout the webinar and during the Q&A. Dan, many thanks for agreeing to talk to us today, and over to you.
Thanks, Peter. As Peter says, so part 1 today from myself on the public sector perspective on developing the UK fusion industry. Part 2 next week, which I strongly recommend, will be done by Nick Walkden on the private sector perspective. So in terms of what I'm going to cover today, so I'm going to start with an overview starting from the UK fusion strategy that the UK government published a few years back, how that relates to UKAEA, my organisation. I'll then dive into the Spherical Tokamak for energy production, STEP, my current programme, talk about how that is acting as a catalyst to develop the industry that we need. Talk a little around the key technical challenges that we need to overcome to commercialise fusion. Then I'll go on to talk about the fusion industry programme, which is drawing together industry into solving the problems that we need to overcome, and then a little about the fusion cluster, which is drawing together the private sector in support of the general endeavour of fusion. And then, as Peter mentioned, there'll be a Q&A at the end, so hopefully there should be time for that. So I thought I'd start by saying what this talk isn't. I'm not going to talk at length about why we're pushing towards fusion or kind of the details of what it is. I will very briefly mention here that clearly it is an endeavour that's leaning into the net zero agenda and the energy security agenda, hence us being sponsored by the Department for Energy Security and Net Zero. However, if you want to explore in more depth about all that background and all the kind of technical intricacies to fusion, then I can point you in the direction of the UK official YouTube, which has an enormous amount of really good videos there, which cover any area you could care to think about for fusion. So anything I don't cover today, have a look there. So as I say, if we start off with the UK fusion strategy and the role that UKAEA play in delivering that. So at the heart of the fusion strategy in the UK are 2 overarching goals. Those are to demonstrate the commercial viability of fusion by building a prototype device, putting power onto the UK grid. And crucially for the talk today, it's about building a world-leading fusion industry. So it's not about just it being a Pyrrhic victory of showing something's technically feasible, but actually seeing how we can translate that into an economic development that is useful to the UK. And so that goes back to October 2021 when the government published that. Underpinning that strategy are 3 core pillars around international, scientific and technology, and commercial leadership. So if we break those down, then the international leadership is all around showing that fusion is possible with our colleagues around the world. Then in terms of science and technology, it's getting to that place where we can show that fusion has gone beyond the possible into the practical. And then where we ultimately want to go is around building a sector that can deliver commercial fusion, both within the UK and perhaps more importantly, globally, capitalising on the expertise that we developed in the UK. So the United Kingdom Atomic Energy Authority, whom I work for, have a mission statement to lead the delivery of sustainable fusion energy and maximize the scientific and economic benefit. So again, we are very much aligned to that UK fusion strategy, that it's going beyond just the scientific through to the economic benefits that we get from fusion. And we can look at that within kind of 9 core areas, which I'll very quickly go over. So in terms of the heart of what we're doing, it's the fusion plasma. So we operate both the jet machine and the massed upgrade machine at our Culham campus. So both of those are looking at how we confine and control plasmas that are going to be relevant to go towards commercial. Moving on from there, we look at the power plant design. So the Spherical Tokamak for energy production program that I'll talk about later is very much part of that, as is our efforts on the European demo program to look at how we can go from scientific experiments through to commercial reality. Underpinning all of this is digital. So we have a real strong drive towards advanced digital AI, modeling, machine learning, all underpinning and making sure that we can both do the design process in the quickest way possible, but also underpins our understanding of the operation of machines and being able to do as much as we can in digital twins before and alongside the operation of plants. Underpinning all of the design efforts is a effort towards fusion technology, so developing the individual technologies that are required to build up the plants that we need. This then goes hand in hand with the optimization of the tokamak performance and the robotics which we require for the maintenance. In terms of the fueling of the device, then tritium is a core component there. So there is a whole effort towards understanding the way that we handle, deal with, extract, and everything else in terms of tritium. Going beyond the technology, obviously underpinning all good technologies, having the right materials, and the regime that we are dealing with is a very harsh one. So getting the right materials right to go in there and developing those, qualifying them, understanding those, and driving down the cost of those is absolutely central to what we're doing. And then I'll just shut my video off a second so you can see this one. Underpinning all this, we need the skills to deliver. So we have a real effort towards apprentice training, but beyond that, looking at all the elements needed to deliver the skills pipeline we need to make fusion a reality. So if we look at what we physically have, then our activities are predominantly based at the Culham campus in Oxfordshire, where I'm based, and we have a range of facilities here. I'm hoping you see my cursor. Yes, you can. So we have OAS, which is the skills centre, which is just recently expanded. We have RACE, which is focused around robotics. We have the massed upgrade, the Spherical Tokamak, that's been the kind of flagship UK tokamak. We have HEAT, which is all around H3 tritium. MRF, which is about the materials research. JET, our world record holding European conventional aspect ratio tokamak, which is just reaching the end of its life. And in addition to the activities on the Culham campus, we have the Fusion Technologies facility, which has recently opened in the last few years in Rotherham, in Yorkshire. And again, I'm going to hide my video. I'm clogging the screen. And we also have the West Burton site, which we will be using to build our STEP device. So on which point I will carry on to talk about that. So diving on and off with my video. So the Spherical Tokamak for energy production. So if we jump back to the UKAEA mission statement, that is to lead the delivery of sustainable fusion energy and maximize the scientific and economic benefit. The STEP mission is more focused, I guess. It's more narrowed down to look at the specifics of delivering that UK prototype fusion energy plant, targeting 2040. So we're location bound in that we're building in the UK. We're time bound in that we're targeting around 2040, and we're focus bound, I guess, in terms of the path to commercial viability of fusion, and that's the area that I focus on. So that commercial pathway is all about having that commercially driven design basis, and underpinning that are three core aspects. So we need to have predictable net electrical production output. We need to get to net electrical, but we need to understand what that's going to be. We need to understand the characteristics of that, and we need to get that to a level where we can scale it ultimately to something that makes sense commercially. We need fuel self-sufficiency, so being able to breathe the tritium that we need in the device to keep the fuel cycle working, and to be able to have all the technologies needed, not just to breed it, but also to feed it, to extract it and feed it back into the machine. And then finally, the maintenance needs to be right. So we need a credible maintenance solution underpinning the STEP device that can then be flowed forward into further commercial devices that follow. And perhaps vitally to the spherical element of the Spherical Tokamak, it is something that has the potential for lower capital costs because it is physically smaller. So on that vein, so to explain what a Spherical Tokamak is, if we look here at a diagram of JET, the Joint European Torus, the device that I just showed you on the map of the Culham campus a few slides back, this has a classical ring donut shape. So it is that kind of ring shape, which takes relatively quite a lot of space for the plasma volume. If we look in comparison to the massed upgrade here, this core element of the plasma here is more of a kind of chord apple shape, and so you're able to squeeze more plasma into a smaller volume, and therefore you can get the energy density up, and you can get your power for the size of the device can be that much higher. That means that you have some challenges in terms of exhausting the power, and so within massed upgrade, one of the key aspects we're looking at here is the diverter. So the diverters are the region in massed U at the top and bottom. It's a double null machine. JET is a single null machine just with a diverter at the bottom. In massed upgrade, they have super expanded diverters, super X diverters, which allow you to spread the energy from the plasma over a much larger area. And obviously, as you go further out, that effect is magnified as you go to a further radius, then you get more and more area to spread the heat over. And so that's what the super X diverter is all about, spreading that area over, spreading that heat over a higher area, which allows you to manage that heat load better. And these sorts of advantages are ones that we will flow through into the STEP device, which, as you can see, has the same sort of geometry. It's much bigger, as you'd expect, but it's the same basic geometry. It's maybe about 4 times the size on a length scale between massed U and STEP. So in terms of the overall STEP program, time-wise, we're currently in the first tranche of the program, exploring the concept design. So within that phase, we're looking at the concept design, we're developing the program, selecting a site that I mentioned before, and sorting out our target operating model going forward into the future tranches. We'll then flow into the detailed design, where we will start our procurement, some long lead manufacture, and develop the site. We'll then flow into main construction and ultimately commissioning and operation in the 2040s. So yeah, I touched on tranches. So we're currently in tranche 1, which comes to an end at the end of this financial year, and we'll be transitioning into tranche 2A, which is the first part of the detailed design, flowing forward from April 24 onwards. And in terms of what we're actually delivering within tranche 1, so it's all about the concept design. So as I touched on before, it's having an ability in that concept design, getting to a single point that meets the 3 key objectives to produce net power to the grid, to demonstrate a plant maintainability route, and to demonstrate that tritium breeding. And underpinning all that, understanding what the program plan is to realize that concept. Second objective was around selecting a site. And I'll talk about that a little bit more in the coming slides. Underpinning all is developing a regulatory standard. So activities in relation to that kind of go on alongside the work within STEP, but STEP will be the exemplar case for proving the regulatory approach using a proportional and appropriate regulatory regime for fusion. And then the final area is around having the model for delivery to go forward from tranche 1 into tranche 2A and beyond. So in terms of the home of STEP, we went out to the nations of the United Kingdom and asked for nominations for potential sites to host the STEP device. We were delighted that we got a huge amount of interest from all around the UK. That interest was distilled down into 5 candidate shortlist sites, from Ardea up in Scotland down to Seven Edge in the southwest of England. And ultimately, we chose the West Burton site in North Nottinghamshire to be the site. And so we selected it within 2022 as intended. And now we're establishing our local presence there and starting to understand what we need to do in terms of developing the site, getting the consenting and permissioning in place, and positioning ourselves allow manufacturing construction to begin. So if we take a little look at the existing West Burton site, so it is an existing coal power plant that we are replacing. So we are very much on there, going from what is currently a fossil fuel site to a fusion site, which we're very excited about. And this hopefully is playing okay. Gives you a bit of a look around the site. So at the right here, we've got the existing coal plant, which has been switched off for the final time and is now in preparations for demolition and remediation. We've got the coal yard where all the coal that went into the coal plant was delivered, which is very helpful infrastructure for us in terms of being able to unload some of our components. We've got an existing gas-fired plant, which will remain. We have all the site apart from that. We have the River Trent running alongside, so that gives us access, which is all good. And we've started mapping out ideas for where our site is. This whole area, this end of site, is all old pulverized flue ash from the coal plant, and so we're looking at characterizing all of that, and all of it mindful of our near neighbours in Gainsborough and the wider local community. So bringing that community with us in terms of developing the program. So in terms of what we're doing at the site now, we're establishing that site team. We're getting the initial layout planned, and we're characterizing to understand the geotechnical conditions to make sure that we build everything appropriately, and as well as building the physical infrastructure, we need to think about building the skills pipeline that we need. So one of the first things we're looking to develop in the area will be the skills centre, similar to the OAS centre that we have at the Culham campus. We'll be looking to have a skills centre in the vicinity of West Burton as well. So I talked a little earlier about the delivery model for the program going beyond this tranche and into tranche 2A, and it's perhaps less clear and obvious than the physical site, but a huge amount of effort has gone into making sure we have the right mechanism to go forward to deliver the program. And so what that has resulted in is the formation of UK Industrial Fusion Solutions Limited, which is a new company limited by shares, entirely state-owned at the moment, but with an opportunity to bring on board investment at future date. So that is managed through our parent department, DESNES, and is part of the wider UKAEA group. Alongside UK Industrial Fusion Solutions will be UK Industrial Fusion Solutions will be a part alongside 3 whole plant partners. So we have the fusion partner, who is UKAEA, who will be supporting on that level. And in addition, we will have 2 further whole plant partners, an engineering partner and a construction partner. These will all form the integrated delivery team alongside some of our strategic supply chain in delivering the program. And we're looking to develop this as very much a one-team approach to realizing the program. And also it's being set up on the basis that we will endeavor to keep a consistent team throughout these partners for the duration of the program. So that clearly involves a huge degree of effort, and great kudos to my procurement colleagues who have been sorting out all the ins and outs, because we'll be shortly going out to tender for both the whole plant engineering partner and the whole plant construction partner. So keep your eyes peeled for that. So that's the STEP program. So hopefully cover that. But if you've got any questions, by all means, chuck them in the chat and we can cover them at the end. So if I lead now onto some of the key technical challenges. So in order to realize fusion and have it in the form of a fusion power plant, which could look a little bit like this. So all the core elements that you'd expect in a standard plant, standard thermal plant, but with its heart, a fusion reactor. There's 5 key challenges. So the first one, the one that everyone kind of knows, is probably about the plasma. So we need to be able to confine a plasma that is 10 times hotter than the sun. So this is footage from within JET. So inside that plasma, you've got a deuterium atom spinning around, and what we want that deuterium atom to do, or we want many of them to do, is to find a tritium atom and fuse together. So those fuse together release a huge amount of energy, mostly in the form of a neutron and also some helium. And those neutrons can then go off and are great for producing loads of energy and therefore electricity. That also brings us to our next challenge, though, the neutron damage that you get at the wall. So this is a nice lattice material, could be steel, could be tungsten, whatever your materials are. And each time one of those neutrons hits that lattice, you get in a degradation of the material. And that's going to change the material properties, going to change the creep, everything there. So getting materials that can deal with that, and also the heat that are in the machine. So the machine in the core, you're getting, as I say, 10 times hotter than the sun. On the walls, you're hundreds or thousands of degrees. At the coils that are controlling everything, you're down to near absolute zero. So you have a ridiculous thermal gradient, and being able to deal with the materials and design for those gradients is absolutely key. So the other thing you need to do, and I touched on it in the designer's step, is breeding tritium. So deuterium you can just get readily from seawater. Tritium doesn't naturally exist, so we're going to breed it. So this is showing you a picture of some nice shiny lithium atoms that are being bombarded by neutrons. Some of those get turned into tritium. So that's kind of a picture of what it looks a bit like in terms of a breeding blanket. That needs to then be separated out and injected back in. So we tend to freeze this as pellets and chuck them back in. So this is like fueling the fire, chucking more wood on the fire. That as long as you're doing that, your reaction carries on. If you stop that, it all stops. So you end up with a very challenging environment inside the machine, which brings you to the last challenge around maintaining the machine and keeping the availability to something that is representative of commercial. So we need to meet all these challenges to get to a commercial device that will ultimately operate, and STEP is very much on that line to that. But we need as much input as we can to resolve these challenges. So yes, so these are the challenges. I think my video was covering up some of them, so I'll let you recap slightly there. So yeah, challenge one being the plasma, keep confining that and keeping it at the right temperature to kickstart the overall process. Two is your materials around that, being able to deal with the neutrons that will bombard them. Three, being able to design for both materials and technologies that can deal with the heat flux. Four, being able to breathe the tritium you need, handle it and get it back into the machine. And five, ultimately being able to maintain a device in a way that makes sense for a commercial device to give it the availability you need for it to make sense commercially. So leading into all these things is the Fusion Industry Program. So the Fusion Industry Program is all about capitalizing on the capabilities that exist within UKAEA and the capabilities that exist within the wider fusion and wider industry to create an ecosystem that we desire for the fusion sector going forward. So if we look at the kind of current state or the starting state, the supply chain, there's some that are quite tokamak focused who've historically worked with us. There's some element of fission alignment. There are a range of current technologies, and a lot of the transaction is kind of procurement based. In step, we're clearly trying to move away from that to a more collaborative approach. But historically, the kind of procurement-based approach has been the model. If we look at the fusion tech companies, you've got a kind of handful of SMEs and spin-outs that are developing this area, but we need more. Those that are there are kind of in the early stages of relationship building between public and private. But there isn't much kind of exchange of use of facilities, and that's something that we're trying to push on. If we look beyond fusion into adjacent sectors, then they may have some understanding of fusion, but not as much as we'd like to be able to capitalize on those abilities. And again, that there's limited knowledge or use of facilities between those areas and our own. And the workforce, there's only certain routes in, and those routes are kind of restricted. So we're trying to broaden those out. So where we're trying to get is this kind of interlinked fusion ecosystem where we have a growth of more fusion tech companies coming in. We're able to grow the workforce and support both those that are working in the private sector and the public sector to build that workforce up, looking to adjacent sectors to use our facilities and have tech transfer coming into our sector and have people and ideas coming into the fusion ecosystem. We want to have an approach that is more concept agnostic. The UK program and within UKAEA has been very magnetic confinement or tokamak focused. We're looking to take a broader approach to look at technologies in the round that could be applicable across the whole spectrum of technologies that could be applied to realize commercial fusion. And yeah, in the supply chain, we're just trying to broaden it out. We're trying to build up the existing companies in there, and we're trying to get new entrants in there. And there's three core schemes that operate under the Fusion Industry Program: the Challenge Scheme, the Voucher Scheme, and the Education Scheme, which I will go through now. So the Challenge Scheme is the kind of big activity within the Fusion Industry Program. It's the kind of core of the funding. And what this is based upon is looking to engage private sector on the challenges that we find most difficult to overcome. So launching those challenges, framing them in a concept agnostic way, so it's as broadly applicable within the fusion sector as possible, and reaching out to the widest possible market of potential companies that could get interested, companies and academia, in fact. So that be from SMEs right through to tier one fusion suppliers and those in fusion adjacent fields. And these are all released through the Small Business Research Initiative innovation competitions. So there have been 4 challenges that have been completed or are in the process of being completed so far. So those have covered quite a breadth of ideas, which I'm sure you'll see are linked back to some of the areas we've mentioned already. So the first one was around digital, so looking at how next generation digital tools can accelerate the design of fusion power plants. The second was around the fueling, so the hydrogen isotopes, so the deuterium and tritium, looking at how advanced production and handling technology can try and drive down the requirements in those areas. The next one was looking at the power plant performance and looking at how innovations in heating and cooling systems, so putting the power in, getting the power out, what innovations there could be in these areas. And the fourth was around availability, so looking at what materials, technology and manufacture options there are to try and drive up that availability of the plant that we're ultimately trying to get towards. So that's the four that have kind of gone into action. And the fifth one, which is we launched at the start of this summer and is just in the process of final contract negotiations, I believe, where they should be announced soon, who's been successful, was focused around lithium technology. So I touched on in that video earlier around the lithium being the thing that we bombard with neutrons in order to get our tritium. So there is a huge amount of activity around that we want to know more about in terms of how to get lithium to the right isotopic enrichment. So for fusion, having more lithium. So lithium is either lithium 6 or lithium 7. Lithium 6 is the constituent that we want more of generally in fusion, because that is a preferential reaction for us to create the tritium. Naturally speaking, lithium is only around 7% lithium 6. It's mostly lithium 7. So understanding how we can drive up that isotopic enrichment in a way that doesn't take too much cost or energy. Then looking in terms of the wider fuel cycle, how we can extract the tritium out of that lithium, and then understanding how we get the lithium into the right form that we need to use within our breeder blanket. So all around conversion and manufacturing. So we were offering up to 1.5 million for prototype development and evaluation, with projects running through to 2025. And as I say, we should be in a position to announce who's been successful for those shortly. So that was all around the challenge scheme. The other areas of the fusion industry program are the voucher scheme and the education scheme. So voucher scheme is around looking at the resources that we have in the UKAEA, which are highly specialised, and looking at how we can utilise those and provide access to those for industry. So we provide a kind of free access or voucher to get access to these to run experiments. And what we're trying to do is make it easy for UK businesses to access our facilities for the benefit of both them and us. So they have that access to those bespoke expertise alongside the technology. So it's not just about them getting access to the facilities in their own right, but having access to our highly skilled team who can ensure that they get best value out of those when they do get access to them. This is a picture in our materials research facility and some of the handling facilities there. And then the final area on the fusion industry program is around education. So as I've touched on a few times, I think there is a need for more science and technology graduates. I mean, there's the need for more science and technology graduates per se, but we have a particular need within fusion. And so we're looking to scale up the routes for talent acquisition. So that falls into two core areas, one around fusion industry placements and another one around careers, information, advice and guidance, and making sure that's relevant and accessible. And in terms of those placements, so we partner with host organizations, and I'm sure my colleagues in the FIT program will be delighted to hear from anyone that's listening today that wants to get involved in this. And these are kind of typically 8-week long programs where we provide sponsorship for successful applicants of up to £3,000 for their subsistence for that. So we just helping to bring more people into the sector through this. Cool. So I think I'm doing all right for time. The fusion cluster was the last thing I wanted to cover today. We have developed a cluster, or rather we are enabling a cluster within the Fusion community. And this is kind of inspired, I guess, by the UK government white paper on industrial strategy, which talks around research clusters attracting inward investment to access knowledge and talent. So there's clearly a thesis behind why these are useful. And so the Fusion cluster brings the right organizations and people together to get to Fusion faster is their kind of key mission. So it's been established just under 2 years now, and it is, as I say, supported by UKAEA, not led by UKAEA, but supported by UKAEA. I guess that's the crucial difference where the Fusion Industry Programme is very much about us kind of trying to direct something that we bring, kind of direct a party that we bring industry into. This is just trying to facilitate something that is more industry-led, but we're trying to kind of create the impetus for it to happen. So the thinking behind it is that fusion energy is too complex for any one organization to achieve alone. Therefore, try and bring together academia, investors, government to try and create those conditions for success and ultimately get to fusion faster. So trying to create clusters that accelerate innovation in fusion. And that's very much at the heart of UKAEA's mission. So in terms of what the Fusion cluster offers, it's all about access to talent, access to facilities, knowledge sharing, showcasing, and I think that's a core part of it, and supporting startups as well. So the Fusion cluster, as I say, it's only just coming to its second birthday, so it's very much in its infancy, and that first phase of it has been around forming, so setting up the advisory board, getting an audience and getting the newsletter, the website, brand identity, and all these things together so they could then go into a range of events, and those have been very good, well attended, and very impactful. So it's all looking very positive. The next phase that we're really coming to now is around demonstrating the value of the Fusion cluster to organizations and governments. So it's got to kind of earn its bucks, I guess, and so that's the drive going forward. But in terms of metrics, it's a very positive picture. So since being started, the cluster's grown from kind of handful through to 200 working in fusion energy all across the UK. So a big concentration in the southeast is probably to be expected, but there is a real significant growth of organizations across the UK who are wanting to get involved in this. And I guess at the heart of this is the private fusion energy developers. So there's 12 of those who are in the fusion cluster who have a declared $2.9 billion in investment. So there's a lot of clout behind the players here, and I'm sure Nick will lead on from here and talk a lot more about that private sector in his talk next week. So in terms of what the partners in the cluster are looking to get from this, then in terms of the private fusion companies, it's an opportunity to raise their profile and the awareness of fusion. Suppliers are looking to work together to create that supply chain ecosystem so they can work together, collaborate potentially, understand what each other are doing. In terms of the investors, they're trying to raise awareness of the commercial opportunities. It provides a clear point of contact for government, for the wider fusion sector, and for academia, it helps identify those next facilities needed and common technological challenges which need to be overcome. So today I've talked you through the UK fusion strategy and UKAEA's role within it. I talked about Spherical Tokamak for energy production, STEP, and how that is acting as a catalyst and a kind of anchor program for the development of a fusion sector in the UK. Talked about the key technical challenges which the industry needs to ultimately solve in order to make fusion a commercial reality, and talked about how the Fusion Industry Programme and the Fusion Cluster are driving towards playing their roles in overcoming those challenges and developing that sector. I think with that, I will go to Q&A.
Thank you, Dan. That was excellent, really interesting. Thanks. We've got a handful of good questions to put to you, but we've got time for more questions. So if you do have a question, please fire it into the chat whilst Dan's having a go at answering these ones. So the first question that came in, Dan, was, what are the plans for actually producing electricity from the fusion energy? Would it be similar to fission with piped cooling water in and around the reactor, converting to steam and turning turbines? How would this look for a fusion reactor?
So thanks. That's a really good question. I didn't go into that level of detail. I'm delighted to. So yes, is essentially the simple answer. In that a fusion energy plant is essentially a thermal plant, and so uses a heat exchanger and a standard balance of plant system alongside that to produce the electricity. It would be lovely to go towards something slightly cleverer with streaming the electrons or something, if you could get electrons rather than neutrons. And there are some schemes that kind of move towards that ultimately. But we've got so many challenges that seems a bit of a leap to go to in one go. So we're looking at more just using the thermal energy from that to produce electricity. Whether it's a classic Rankine cycle, or whether you with steam, or whether you go to something a little bit more advanced like a supercritical CO2 Brayton cycle, is something that we're considering, and actually we're going. Our current design point is actually nearer to the kind of Brayton cycle, so it's a gas-based system, but it is in essence a standard kind of thermal to electrical conversion cycle with unfortunately the losses you get in those systems.
Great, thanks, Dan. Next one is about how the fusion reaction is initiated. So yeah, the question is how do you initiate the fusion reaction? Is it laser or particle bombardment? And is the reaction that follows from that continuous or pulsating?
So the approach that we are using within STEP and more broadly in the kind of UKAEA approach is a magnetic confinement approach. So it is has coils, electromagnetic coils that are controlling the plasma, and they're also used to start up the plasma in our current concepts. Having said that, one of the challenges in the spherical tokamak is the inside of the machine gets very, very busy. So the solenoid, the coil that goes down the middle of the machine, you would like that to be as small as possible. So that's certainly one of the challenges.
Okay, thanks, Dan. Okay, we've got a question about lithium and sourcing lithium. In fact, a couple of questions about sourcing lithium. So, can you say a little bit about where the lithium would come from? Whether the UK is a potential source of this material, so the initiative to mine lithium from Cornwall, for example, and about whether you'll be considering the ethical aspects of where the lithium comes from.
Absolutely, that's a really good question. Sorry, let me just take a glass of water. So yeah, the sourcing of lithium and the ethics around that is definitely one that we are very aware of. So we have had some conversations with some of the lithium producers in the UK, both those looking at mining it and also those considering extracting it from recycling batteries, etc. So we are very interested in trying to develop a UK, well, an integrated UK lithium approach. So yeah, so I guess the best answer is that it's a bit of a work in progress in terms of where we end up, but we are involved in dialogue with a range of parties in the UK, and we are very keen to make sure that the credentials of any lithium going into STEP are appropriate, and that we develop a lithium sector within the UK that is joined up between what is going on in the wider battery development arena, as well as what we will ultimately require for fusion.
Okay, great. Thanks, Dan. I guess the overall volumes of lithium that will be consumed aren't enormous.
So it's not enormous. If you look at it relative to the global volumes for battery production, yeah, it's small, insignificant, but it's still potentially in the tens to hundreds of tons per device. So it's a lot to handle, but within the wider global sphere, yeah, it is smaller, but it is in terms of enrichment, then fusion or fission, if you go to molten salt, where they require lithium-7, very high purity, the enrichment in those areas is the volume of that dwarf any other need. So there is no other driving need for enriched lithium beyond those sort of technologies.
Okay, great. Thanks, Dan. So we have a question. How much energy is produced from fusion as opposed to other generation methods such as fission? And I guess this would be on a kind of land take basis.
So it's not really something. I mean, at the moment, there is no functioning operating fusion plant. Much as I'd love them to have got to that stage. So the STEP program will be putting somewhere in the region of 100 megawatts onto the UK grid around the 2040s. Others within the private sector, I'm sure Nick will cover next week, are targeting even more ambitious timescales. In terms of the energy density, if you looked at purely at STEP, it doesn't look great, but you got to remember it's a prototype. So we would anticipate something similar to the size of STEP being able to put out around 10 times what the prototype would put out if it were to be a truly commercial plant, at which point you're getting somewhere similar to the kind of energy per site area as you would get for a fission plant, I'd guess, roughly speaking. In terms of the core energy density you're getting, it's enormous, but obviously there's a lot of infrastructure around that plant. But yeah, the overall energy density for a mature commercial fusion plant is more along the lines of a fission plant than, for example, solar or wind, where obviously you have to have much larger arrays of those to get an equivalent volume.
Okay, excellent. Thanks, Dan. Questions are still coming, which is terrific. Okay, so Dan, you mentioned the material deterioration due to neutron impacts. What is the current longevity of the materials subjected to these impacts?
So we talk in terms of full power years, so that the amount of time that for the operation of the plant that it can be withstand. So we are looking, and it is something where we are developing these technologies. So I think it's something where the materials are not necessarily where they need to get to for a fully commercial. But one of the main challenges that we have in doing this is that because we don't really have a fully representative environment until we have an operational plant, will be a lot of unknowns, and that's where we have to do as much as we can within digital tools and so forth to operate those. But they're in kind of handfuls of years that we would think we could probably expect to get, but we would like to get those into sort of more like tens of years if we could, to be able to try and up the overall availability of the plant to minimize the kind of downtime that we need to have. But obviously with all of it, the plant will only be up as long as its weakest link is up. So we need to make sure that we cover all elements of both the materials and the technology development.
Okay, excellent. Thanks, Dan. So we have a question from Australia.
Excellent.
Yeah.
Thank you for tuning in.
Yeah, absolutely. So coming from Australia, is the plan to make this a solely UK development, or is there an opportunity, somewhat like the F-35 Joint Strike Fighter, where other countries are invited to join the party?
So I think within UKAEA, if we kind of go back to the original kind of public sector strategy on fusion, international collaboration is absolutely part of what we are trying to do. So to just frame this, we have and continue to participate in UK in the European demo program. So we are involved in that and continue to do so, and are very pleased to continue to do so. We are striving to find a route to remain involved within the ITER program. So that's something that we're currently trying to work out how we're doing. More generally, we are very active internationally and seek international input to our work. So yes, and I guess if we talk in terms of the STEP program, it is a UK government funded program, and it has at its core the intent to develop a UK fusion industry, but we are not so foolish as to assume that we could do this without engaging any of a range of international players who have their own strengths that they can bring. So when we come to the tender that will be going out shortly for the engineering and construction partner, again, it is about developing UK capability, but it is not something that is exclusively going out to UK companies. So there is that aspect, and the longer term way that STEP has been set up with UK Industrial Fusion Solutions as a company limited by shares opens us up to investment, and that could be from in the UK from the private sector, but it could be from quarters around the world. So we are very open and interested in those sorts of things.
Great, thanks, Dan. That fits quite nicely into another question we've had, which is about current UKAEA involvement with ITER. And is there a relationship, or are the relationships in place to take the lessons learned from ITER and apply them to STEP?
So the exact current status of UK relationship to ITER is that, so as of a few weeks back, when we had the wonderful announcement of Horizon 2020, UK associating, alongside that the announcement of the status of the Euratom position that the UK wouldn't associate, but would find a different route, or existing route, in fact, into the EU demo program. What that has led to is that we are not directly associated to ITER at the moment. However, we were unable to progress that in parallel, because the route that we previously had was via Euratom. So we're now looking to route similar to, in fact, funny enough, your friend from Australia, to looking at possibly having a similar model to Australia to getting into ITER. So that's something that we are in the process of considering and trying to find our appropriate route in. In terms of the lessons learned, there is a lot of knowledge exchange across the Fusion community. So whether UKAEA are actively involved in ITER or not, there is a lot of information exchange between ourselves and other organisations around the world, both from people who are actively involved in them or those who have historically been involved with them. So yes, we are definitely taking on board the lessons from ITER, and one of the real strengths of, notwithstanding our interest in having others join us in the STEP program potentially in the long term, one of the strengths of STEP is because it is a single nation-led endeavour. It does allow a certain level of streamlining in terms of how we do things. So that has definitely been an advantage for us.
Okay, great. We've got 4 minutes left, and we've actually got one last question. So all working quite neatly. So last question is, as a young engineer in the building services industry, how big of a jump or likely would it be to work for UKAEA? I would imagine UKAEA requires building services, mechanical and electrical engineers to help with the construction and cooling processes.
I mean, I'd say it's probably not as big a leap as you imagine. It's probably the simple answer. There are, whilst at the heart of the fusion experiment or commercial plant, whatever you're coming up with, you are doing things with conditions that are mind-blowing. Around that is a lot of kit that is very standard, and intentionally so. We generally will design with kit that is standard if we can, because why reinvent the wheel, right? So we will build in as much industry standard equipment for anything that is away from the core of the fusion device as we can. So I would expect that the questioner would find a lot of commonality to what they currently do. We have a lot of electrical, mechanical, building services activities that we need, and yeah, I'd advise them to look on our vacancies. I'm sure we have some vacancies.
Brilliant, thanks, Dan. Yeah, that is all the questions in the list. So thank you so much for answering those, and thank you for everyone who put questions in the chat. Hopefully everyone who's come along today will come to part 2 next week, next Tuesday, and there will be opportunity then to ask more questions. So if anything occurs in the meantime, you can bring questions along to that one. But apart from that, thank you to everyone for coming along. Thank you to Emma Pateman of the IMechE for organising this. And at that point, we'll close the webinar.
Brilliant. Thank you all.